determine the number of parallel runs required for 2000 amps feeder using 500 THHN kcmil conductors, it's essential to understand the National Electrical Code requirements for conductor ampacity and adjustment factors. In this scenario, we have 4 current carrying conductors in each raceway, which necessitates the application of an ampacity adjustment factor as outlined in Table 310.15 (V2) of the National Electrical Code. This table provides adjustment factors for the ampacity of conductors based on the number of current carrying conductors in a raceway or cable. With 4 current carrying conductors, an adjustment factor of 80% must be applied. The 90 degrees Celsius ampacity of a 500 kcmil copper conductor with THHN insulation is 430 amps according to the appropriate ampacity table, typically Table 310.16 of the National Electrical Code for conductors rated 0 to 2000 volts. However, the adjusted ampacity must be calculated to account for the 4 current carrying conductors in the raceway. To calculate the adjusted ampacity, multiply the 90 degrees Celsius ampacity by the adjustment factor. In this case, 430 amps multiplied by 0.80 equals 344 amps. Therefore, the adjusted ampacity for each 500 THHN kcmil conductor in this installation is 344 amps. To determine the number of parallel runs needed for the 2000 amps feeder, divide the total feeder current requirement, which is 2000 amps, by the adjusted ampacity of each conductor, which is 344 amps. This calculation is 2000 amps divided by 344 amps, resulting in approximately 5.81. Since you cannot have a fraction of a parallel run, you must round up to the nearest whole number. Therefore, this installation will require 6 sets of 500 kcmil conductors for the 2000 amp circuit. In summary, firstly, identify the 90 degrees Celsius ampacity of the 500 kcmil THHN conductor from the National Electrical Code table. Secondly, determine the ampacity adjustment factor based on the number of current carrying conductors in the raceway, which is 80% for 4 conductors. Thirdly, calculate the adjusted ampacity by multiplying the 90 degrees Celsius ampacity by the adjustment factor. Fourthly, divide the total feeder current requirement by the adjusted ampacity to determine the number of parallel runs needed. Finally, round up to the nearest whole number to ensure the feeder can safely carry the required current. It's critical to adhere to the National Electrical Code guidelines to ensure the safety and reliability of electrical installations. Always consult the latest edition of the National Electrical Code and consult with a qualified electrical professional to ensure compliance and proper installation practices. Remember to consider other factors that can affect conductor ampacity, such as ambient temperature and conductor bundling, when determining the appropriate conductor size and number of parallel runs. This calculation provides a fundamental understanding of how to determine the number of parallel runs needed for a feeder circuit. The National Electrical Code outlines specific requirements for conductor ampacity, dating, and installation methods to ensure electrical systems are safe and reliable. Understanding these requirements is crucial for electrical engineers, contractors, and anyone involved in electrical installations. The ampacity of a conductor is the maximum current, in amps, that a conductor can carry continuously under specific conditions of use without exceeding its temperature rating. This is a fundamental concept in electrical engineering and is governed by the National Electrical Code, specifically Article 310. The National Electrical Code provides tables, such as Table 310.16, that list the allowable ampacities of insulated conductors rated up to and including 2000 volts, based on the conductor's insulation type and size, and the ambient temperature around the conductor. These ampacity values are based on certain assumptions, such as the conductor being installed in a specific manner, like in free air or in a raceway. However, in real-world installations, several factors can affect a conductor's ampacity, necessitating adjustments to the values found in the National Electrical Code tables. One of the most common factors is the number of current carrying conductors in a raceway or cable. When multiple current carrying conductors are bundled together in a raceway or cable, the heat generated by each conductor can raise the overall temperature within the raceway or cable. This increased temperature can reduce the ampacity of each conductor, as higher temperatures can degrade the insulation and increase the risk of electrical failure. To address this, the National Electrical Code requires that the ampacity of conductors be adjusted when there are more than 3 current-carrying conductors in a raceway or cable. The adjustment factors are provided in Table 310.15. B2a. These factors reduce the allowable ampacity of each conductor based on the total number of current-carrying conductors. For example, if there are 4 to 6 current-carrying conductors in a raceway, the ampacity of each conductor must be reduced to 80% of its value in Table 310.16. If there are 7 to 9 current-carrying conductors, the ampacity must be reduced to 70%, and so on. Another factor that can affect conductor ampacity is the ambient temperature around the conductor. The ampacity values in Table 310.16 are based on an ambient temperature of 30 degrees Celsius or 86 degrees Fahrenheit. If the ambient temperature is higher than 30 degrees Celsius, the conductor's ampacity must be reduced to compensate for the increased heat. The National Electrical Code provides correction factors in Table 310.15. B1 that can be used to adjust the ampacity for different ambient temperatures. For example, if the ambient temperature is 40 degrees Celsius and the conductor has a temperature rating of 90 degrees Celsius, the correction factor might be 0.91. This means that the conductor's ampacity must be reduced to 91% of its value in Table 310.16. In addition to these general factors, there are also specific rules for dirtying conductors in certain situations. For example, conductors installed in underground ducts or conduits may be subject to dirtying due to the difficulty of dissipating heat in those environments. Similarly, conductors installed in direct sunlight may need to be deaerated to account for the additional heat from the sun. Parallel conductors are often used in electrical systems to increase the ampacity of a circuit. When conductors are connected in parallel, the current is divided among the conductors, allowing the circuit to carry a higher total current than a single conductor could handle. However, the National Electrical Code has specific requirements for installing conductors in parallel. Firstly, all parallel conductors must be the same length, conductor material, size, insulation type, and termination method. This ensures that the current is evenly distributed among the conductors. Secondly, the parallel conductors must be installed in the same raceway or cable. This helps to ensure that all the conductors are exposed to the same ambient temperature, which is important for maintaining equal current sharing. Thirdly, the overcurrent protection device for the circuit must be sized to protect the smallest conductor in the parallel set. This ensures that no single conductor is overloaded. When calculating the ampacity of parallel conductors, the ampacity of each conductor is simply added together to determine the total ampacity of the circuit. However, the adjustment factors for the number of current-carrying conductors and ambient temperature must still be applied to each conductor before adding the ampacities. For example, if you have 3 500 kcmil THHN conductors in parallel, and each conductor has an adjusted ampacity of 344 amps, the total ampacity of the circuit would be 344 amps times 3, which equals 1032 amps. When designing an electrical system, it is important to carefully consider all of these factors to ensure that the conductors are properly sized and installed. Failure to do so can result in overloaded conductors, overheating, insulation damage, and even electrical fires. It is also important to consult the latest edition of the National Electrical Code and to work with a qualified electrical professional to ensure that the installation meets all applicable codes and standards. In the specific scenario you presented, the question involves determining the number of parallel runs required for a 2000 amps feeder using 500 THHN kcmil conductors with 4 current-carrying conductors in each raceway. The key steps in solving this problem are as follows. Firstly, determine the 90 degrees Celsius ampacity of a 500 kcmil THHN conductor. According to Table 310.16 of the National Electrical Code, the 90 degrees Celsius ampacity of a 500 kcmil copper conductor with THHN insulation is 430 amps. Secondly, determine the ampacity adjustment factor based on the number of current carrying conductors in the raceway. Since there are 4 current carrying conductors in each raceway, the adjustment factor is 80% according to Table 310.15 (E2) of the National Electrical Code. Thirdly, calculate the adjusted ampacity by multiplying the 90 degrees Celsius ampacity by the adjustment factor. In this case, 430 amps times 0.80 equals 344 amps. This is the adjusted ampacity for each 500 THHN kcmil conductor in this installation. Fourthly, divide the total feeder current requirement by the adjusted ampacity to determine the number of parallel runs needed. In this case, 2000 amps divided by 344 amps equals approximately 5.81. Finally, round up to the nearest whole number. Since you cannot have a fraction of a parallel run, you must round up to 6. Therefore, this installation will require 6 sets of 500 kcmil conductors for the 2000 amp circuit. This calculation demonstrates the importance of considering ampacity adjustment factors when designing electrical systems. By properly directing the conductors based on the number of current carrying conductors in the raceway, you can ensure that the conductors are not overloaded and that the electrical system is safe and reliable. In addition to the factors discussed above, there are also other considerations that may affect the number of parallel runs required for a feeder circuit. These include voltage drop, short circuit current rating, and the available space for installing the raceways. Voltage drop is the reduction in voltage that occurs along a conductor due to its resistance. The National Electrical Code recommends that voltage drop be limited to 3% for feeders and 5% for branch circuits. If the voltage drop in a feeder circuit exceeds these limits, it may be necessary to increase the size of the conductors or to add more parallel runs to reduce the resistance of the circuit. Short circuit current rating is the maximum current that a conductor can safely withstand during a short circuit. The conductors in a feeder circuit must have a short circuit current rating that is high enough to withstand the available fault current at the point of connection. If the short circuit current rating of the conductors is too low, it may be necessary to increase the size of the conductors or to add more parallel runs to increase the overall short circuit current rating of the circuit. The available space for installing the raceways can also affect the number of parallel runs required. If there is limited space for installing the raceways, it may be necessary to use smaller conductors and more parallel runs to fit the conductors within the available space. In summary, determining the number of parallel runs required for a feeder circuit is a complex process that requires careful consideration of a number of factors, including conductor ampacity, adjustment factors, voltage drop, short circuit current rating, and available space. By carefully evaluating these factors and consulting with a qualified electrical professional, you can ensure that the feeder circuit is properly designed and installed to meet the needs of the application. Remember that the National Electrical Code is a comprehensive set of standards that governs the safe installation of electrical systems. It is essential to stay up to date with the latest edition of the National Electrical Code and to follow its guidelines when designing and installing electrical systems.